if I flip the states of a non-deterministic, I do not necessarily find the complement. Is it true that flipping the states of a non-deterministic will recognize the complement of the language? No. It has to be deterministic. For example, here is an automaton, right? I want it to be non-deterministic. Yeah. What's my alphabet is AB. AB. This is non-deterministic because the B arc is missing. What's the language recognized by it? A star. A number of A's. So the language is A star. Now let's flip the states. What's the language recognized by it? Right, the empty set. Well, is that the complement of A star? No. If you take A star, the other strings, for example, AB is not in A star, but he's not here either. So by flipping states of a non-deterministic, I do not necessarily find the other strings. AB is not in here in the original one. Well, it's not in here either after I flip the states. I did not find the complement, right? So when we said last time that flipping the states of an automaton recognizes the complement of the language, it has to be a deterministic automaton for that to work. So this one gives you an algorithm to find an automaton for the intersection of two regular languages. What's the algorithm? Okay, M1 is regular, build an automaton for it, but don't build a non-deterministic one. Always convert it to a deterministic automaton. So get the deterministic for M1. Flip the states. Get the deterministic for M2. Flip the states. Take the union, which means new node, empty, empty. But this is non-deterministic now. So don't flip the states of that. After you took the union, convert it to deterministic again. And then flip the states, the last complement. That's the algorithm for finding the union of regular languages, finding an FSA. Right? Okay, so I wonder, in the case of context-free grammars, can I make an argument like that, you know? Maybe if I have, this is context-free, this is context-free. How about the intersection? Maybe there is a way to construct a PDA. Right? Is it true that the intersection is also context-free? In the case of regular languages, that's false. It's not always the case. You can intersect two context-free and you come up with something that is not context-free. Actually, this is not context-free. A and B and C and is not context-free. Now, how would you show that you cannot build a PDA for it? You might, let's try to build a PDA for it. I want to recognize these strings, right? Okay, why doesn't this work? I'll start. If I see A's, I'll push them. Okay. And actually, I'll push double the number of A's. If I see one A, I'll push two. I'm thinking ahead. So if I see an A, I'll push two A's. So I'll do that. I'll change state. If I see a B and I have A on the stack, I'll pop it. Right. Now, let's say I have 4 of each on the table. I pushed 8 A's. With the 4 B's I popped. How many A's I got? 4. So I'll change state. And if I see a C and I have an A, I'll copy. Right? Did I just build a PTA for this? Will this work? If it did, it means this is context free. How I got this, you know, when I ask the students, say, yeah, you can do it here. They give me this automaton. This will do A, N, B, N, C, N. What's wrong with this?
It recognizes
More than just those. For sure he will do all those, right? Because he will do all those. But he does something more than that. Right? This is not the language recognized by him. Something more is the language. Give me a string not in here that will be recognized by this guy. A what?
ABB.
Yeah, ABB. Because with A you push two A's, you cancel the stack, empty stack with the C's, with the B's, you go here, you're good. You don't need any C's.
So what do you do?
Or even, here's another one. How about this? Will you also do that? Sure. You push 4 A's, you cancel one of the A's, and you go the last stage, you cancel the other 3. This also works. So this automaton, that's not his language. What is his language? It's the language of this guy is AI, BJ, CK, where J plus K equals I, correct. If the number of B's and C's together,
It's 2i.
2i, 2i, right? Right? If the number of B's and C's together is twice as many I's, as many A's, this is a totally different language. Right? So this failed. This is not it. That's not the solution. Right? Can you build a PTA to do exactly this language? It turns out no, you cannot, no matter how hard you try. But how do you prove that? I give you 3 months. Keep trying. You will not be able to. That's not the proof. Maybe we're not smart enough, you know. Maybe he could do it in 5 minutes, but we never asked him. You know. How do you prove something is not context free? There is a version of the Pampilima for context free languages. That you use to prove things like that. If you suspect something is not context free, that will be a way to prove it. Okay. Okay, this is the Pampilima for context free languages. If AL is a context free language, it's similar to version 2 of the Pampilima for regular lengths, right? Then there is some number p, k, whatever. So that for all strings of length more than k, you, instead of finding x, y, z, pumping the middle, now you say you can find actually 5 strings. Say u, v, x, y, z. So that any string can be written as a concatenation of 5 strings with the property that if you pump the v and the y, the second and the fourth, so now you're pumping in 2 positions, you will remain in the language. Right? So you can write any string as concatenation of 5, so that when you pump the second and the fourth, as many times as you want, you stay in the language. So if it's context free, you can do that. Okay? That's the Pampilima. Then, and by the way, you also have a version 1 of the Pampilima for context free corresponding to version 1 of the regular. In version 1, you don't need to bother with that number p, you know. Here we can use version 1. If this was context free, then by the pumping lemma, I could find an x, a y, a z, a w, what should we call it, v, so that this is in the language, and so that if I pump this, if I pump that, equal number of pumps, you know, nn. Was it equal in the lemma? Yeah. Okay. I still stay in the language. So if it was context free, I could do this. I could find the strings. Okay, but x, y, z, w, v, those are the guys I'm pumping, right? Is in the language means this string for n1, right? This is in the language means it looks like a number of a's, a number of b's, a number of c's, equal number. Right? X, Y, Z, W, V must look like that. Okay, now, what do? It's the same arguments, but now you have to worry about two variables. So it's like a nested loop argument. You start examining all possible choices for Y, and for each choice for Y, you have a number of choices for W. And if you can reject all of them, you go to the next possible Y, all choices for W, until you go through the double loop and you reject all possible choices. Since this looks like that, right, what could Y be? Okay, X could be some of those, Y some of those, right? Well, Y could be a section of A's. That's the first case, right? So X will be over here, Y could be there. So case 1, Y could be some A's. Okay, if Y is some A's, what could W be? Well, Z could be some more A's, and W could be some A's. Or W could be some A's followed by B's. Or only B's. Or B's with C's. Or only C's. Do you follow? That's why I say nested loop. If Y is A's, what is W? Well, W could be only A's also. Let's make this. W could be somewhere here. But in this case, right? So of course then Z would be A's also, and V would be what's left. But I don't care about the values of these guys. I don't care about the things I found. Okay, so if that was the case, if this was Y and this was W, then when I take X, Y squared Z, W squared V, is this in the language? I'll go and square the Y and square the W. Is this in the language? No, why not? More A's. You just increase your number of A's, you double. So you increase them. That's not in the language. So case 1 is rejected. Y and W could not be A's. Okay? The pumping sections cannot be A's. It won't work. Okay, case 2, nested loop. Leave Y the same, go to the W. Okay, W maybe is not only A's. What else could it be? Well, it could be over here. So some A's followed by some B's. So AL, B, J or something. This could be W. Right? If that was the case, and you square Y and you square W, the whole thing is X, Y, Z. X, Y, Z, W, V. Okay? Now, what if I go and square this and square this? Will I be in the language? No, for many reasons. First of all, the C's did not change, I just increased my A's here. It's not equal number. Okay? Even worse, if I have AB's and you square them, I find AB's, AB's. I'll have A's following the B's. That's also fine. It's not in the language. A's cannot be after the B's. So this is not in the language. Okay, what else? You got the idea. So it's the same argument, but more cases to think about. Language, take the complement of it. Is this context free? Not necessarily. It might be, but it might not be. Okay. All right. How can you verify those two statements? The first one you already did. You said take L1 to be AN, BN, CK. Take L2 to be AK, BN, CN. Right? Any number of C's but equal number A and B's. Okay? Equal number of B's and C's. Take the intersection. All right? You said before the intersection is AN, BN, CN, equal number of each. And by using the papillema, you can show this is not convex free. So the intersection of convex free is not necessarily convex free. It might be, in some examples it is. Okay. Now, how about the complement? So that's the argument for the intersection. It's not true that the intersection is convex free necessarily. It might or it might not be, depending on the case. The complement of convex free. Is it convex free? Here is how you make this argument. I want to express the complement in terms of what? Unions and intersections. I cannot do that. And difference, right? Actually, let's do that. Let's express the intersection. It is an easier way to. Let's express the intersection in terms of unions and complements, like you did before for the regular case. Okay, what's this? Right? Okay. Now, let me ask you something else. We forgot to examine this case. If L1 is convex free and L2 is convex free, is it true that the union is convex free? The union of two convex frees, is it convex free? That's true. Why? If L1 is convex free, you can do a PDA for it, right? L2 is convex free, you can do a PDA for it. Okay, I want to recognize the union. Give me a PDA for it. New state. And what do I do on the stack? Nothing. So it's the same algorithm as for the union of regular, but you're ignoring the stack. I can stick a new state, and this is a non-deterministic PDA that does the union. If something was in L1, you can go that way and do it, or you can go that way and do it. The union of convex free is convex free. Now, the complement of the convex free is not convex free. What's the argument? By contradiction, a proof by contradiction. If it was true that the complement of a convex free is convex free, if that was true, then look here. If L1 was convex free, well, if it was true that the complement is, that would be convex free. That would be convex free. The union is convex free. The complement of a convex free, if that was true, this would be convex free. So this would be convex free. So if it was true that the complement of convex free is convex free, then it would be true that the intersection of convex free is convex free. But we know this is not true. We just gave an example. Proof by contradiction.